So we learned about oxidation states, and now we're going to learn how to use that to identify redox reactions. So remember that we talked about oxidation as being a loss of electrons. If you lose electrons, that means that the oxidation state increases. Losing electrons makes it a positive ion, and that would have a more positive oxidation state. Reduction is a gain of electrons, which would be a decrease in oxidation state. So oxidation means the oxidation state gets bigger. Reduction is a reduction in the oxidation state. So there's oil rig, and you can also think of it this way. Looking at this example where we have two nonmetals reacting, we have copper and sulfur forming carbon and sulfur, forming carbon disulfide. To predict whether this is a redox reaction or not, we can't look at charges because there's no ionic charges. So we look at oxidation states. Here we have two elements. They both have oxidation states of 0. Over here in carbon disulfide, we have to use that list, Fa765, to decide what the oxidation states are. There's no fluorine, there's no hydrogen, there's no oxygen, there's no group 7. We're running out of things. There's group 6. Sulfur's in group 6. Sulfur gets what it wants as an oxidation state. So sulfur as an ion would be -2 minus, so it will choose -2. So it gets to be -2. There are 2 of them, so the carbon has to be +4. Identifying those oxidation states, then we can look and see what happened to the carbon. The carbon went from an oxidation state of 0 to +4. That's an increase in its oxidation state. Sulfur went from 0 to -2. That's a reduction in the oxidation state. So carbon was oxidized, sulfur was reduced. Any questions? Deathly silence. Let's practice. Use oxidation states to identify the element that is oxidized and the element that is reduced in the following redox reaction. So we're going to go through, this will give us some practice on oxidation states. We're going to go through and assign oxidation states to every element in the reactants and the products. So the first reactant is tin. What's the oxidation state for tin, the element? 0. So that's 0. Here we have nitric acid. So we've got hydrogen, nitrogen, and oxygen, 3 nonmetals. So we say Fa765. There's no fluorine, but there's hydrogen. What would hydrogen choose? What would a hydrogen ion have for its charge? +1. It's in group 1, right? So the hydrogen is +1. So after hydrogen comes oxygen. What does oxygen choose? -2. And then the nitrogen has to be whatever makes up the difference. All the oxidation states have to add up to the overall charge of the species. This is a neutral molecule, so all the oxidation states add up to 0. Each of the oxygens is a -3. So, sorry, -2. Oh my goodness. So there's 3 of them. So that's a total of -6. And then we've got this +1 from the hydrogen. So what does the nitrogen have to be? +5. So the nitrogen's going to be +5. So I'll erase these because we don't need those. So the nitrogen's +5. Because we've got the 1 and the 5, that's a total of +6. And then there's 3 -2s, okay? Isn't this fun? At 8 o'clock in the morning? Yeah. Okay, here we have SNO2. Is that a molecular or an ionic compound? It's an ionic compound, right? So we can look at the ion charges. That's the easiest way to figure out what the oxidation states are. So oxygen here is an ion. And what's the charge on an oxide ion? 2 minus, right? So, bless you, it's going to have an oxidation state of -2. What's the charge on the tin ion? It's not on the periodic table. Plus 4. I know your brains are still waking up. It's okay. So we have 2 negative 2 charges. That's a negative 4. And so this one tin ion must be a plus 4. So for monatomic ions, the oxidation state and the charge are the same number. They're not the same thing, but they're the same number. Here we've got nitrogen dioxide, 2 nonmetals. Who gets first priority? Oxygen. Fe765. Fluorine, hydrogen, oxygen. Oxygen always chooses negative 2. So what does the nitrogen have to be? Plus 4. Now sometimes students get confused by these coefficients. The coefficients are for balancing the equation. They have nothing to do with oxidation states. We're looking at the NO2 here. And then last, we've got water. Who gets first priority, hydrogen or oxygen? Hydrogen. What does it want? Plus 1. So what's the oxygen? Negative 2. Any questions about how we got the oxidation states? Okay. So to identify what's being oxidized and what's being reduced, there has to be one of each. We're going to look at each element and see how their oxidation state changes from where they are as a reactant to a product. So let's just start with the first one. Here's tin going from 0 to plus 4. Is that oxidation or reduction? That's oxidation. The oxidation state is going up. So that's oxidation. And let's see, here's hydrogen, and over here hydrogen's plus 1. So that one didn't change at all, so we could just kind of ignore him. Here's nitrogen plus 5, and there's nitrogen plus 4, so that's different. Is that oxidation or reduction? That's a reduction because it went from plus 5 to plus 4. It got reduced, right? And you can have more than one element being oxidized and or reduced. So we got to check the other ones here. Here's oxygen is minus 2, and then oxygen is all over the place over here. Minus 2, minus 2, minus 2. It didn't change. So it just hung out. So the tin was oxidized, the nitrogen was reduced. If we think of it in terms of gaining and losing electrons, the tin went from a neutral atom to a positive 4 ion. It did so by losing electrons. Oxidation is loss of electrons. Oil. Reduction is gain of electrons. So the nitrogen here didn't gain electrons. It didn't become an ion, but it gained electron density. And that's why we need the oxidation states, is so that we can see that. Anybody have any questions? So in a redox reaction, we have to have oxidation and reduction at the same time in the same reaction, because if an atom loses an electron, those electrons have to go somewhere. They can't just, go to the shelter. So just to make matters a little more confusing, we not only have things that are oxidized and reduced, but we have agents. So the reactant that reduces an element in another reactant is called the reducing agent. So let's just pull back from this and think about Hollywood. Okay, so in Hollywood you have movie stars, and then you have the agents. And what do the agents do? Do they star in the movies? No, they help the movie stars get the part, right? So the reducing agent doesn't get reduced. The reducing agent helps the movie star, the other thing, get reduced. Okay? So the reducing agent is causing something else to be reduced. And likewise, the oxidizing agent is causing something else to be oxidized. Okay? Well, let's practice that. First, identify, is this a redox reaction? And then for the redox reactions, identify the oxidizing agent and the reducing agent. So let's start with number 1. So here we have a metal and a non-metal. So that's a big clue that this is a redox reaction. Because if we look at what's happening here, we have atoms and molecules, they're neutral elements, and here we have an ionic compound. Ions are being formed. You can also identify this by looking at the oxidation states and seeing our oxidation states changing, and we'll find that they are. So this is a redox reaction. Let's do this one in terms of ions. What's the charge on a lithium ion? +1. And on a chloride ion? -1. So here the lithium went from neutral to a positive charge. If we're looking at oxidation states, it went from 0 to +1. Or thinking about electrons, lithium lost an electron to become lithium plus. So is lithium being oxidized or reduced? Oxidized. Oxidation is loss of electrons. So if it is oxidized, then the other one here must be the oxidizing agent. The chlorine is causing the lithium to be oxidized. So this is the oxidizing agent. So lithium is being reduced. What's happening to the chlorine? Going from 0 to -1. It's a gain of an electron, right? Okay, tell me when I do this. That's dumb. Yeah. No, see, yeah. Oh, gosh. Okay, lithium's oxidized. We just said that, and then I write the wrong thing. So chlorine is being reduced. I wish I could say I did that just to see if you're paying attention. Can't do that. So chlorine's being reduced. So what kind of an agent is it? It's an oxidizing agent because it's causing the lithium to be oxidized. So this is our oxidizing agent. What's the reducing agent then? It's the lithium. So they're working on each other. You've got one oxidizing agent, one reducing agent. I know that's confusing. I'm sorry, I didn't make this up. Let's look at number 2. Is this a redox reaction? Are things changing their charges? Look at aluminum. What's its charge here? +3, and what's its charge here? 0. So it's becoming an ion. So there's electrons being transferred around. It is a redox reaction. So aluminum going to aluminum +3, gaining or losing electrons? Losing electrons, okay? So if it's losing electrons, oxidation is loss of electrons. It's being oxidized, so what kind of an agent is it? The reducing agent. The way I'm talking you through this right now, that's how I would answer this question, except I would do it in my head, because it's embarrassing to say all of that out loud. Okay, let's look at this one. SN2+, and what's it's doing over here? SN0. So did it gain or lose electrons? It gained electrons. Reduction is gain of electrons. So if it's being reduced, what kind of an agent? Oxidizing agent. So this is the oxidizing agent. You see how that works? Any questions? Let's look at number 3. Yeah.
So if there's no charge on left, then they're neutral.
Right. This is an element. So unlike something like CO2, there's no charges here either, but there are non-zero oxidation states. But if you have an element all by itself, its oxidation state is 0. Even if you have something like Cl2, diatomic molecule, but those two chlorines are the same. How are you going to convince one to be -1 and one to be +1? They're not going to do it. They're both going to be the same. Any other questions? Okay, number 3. Is this a redox reaction? We have ionic compounds, right? So look at the charges on the ions. They're the same. Pb is +2 here, and it's +2 there. Lithium is +1 and +1. This is -1 for chlorine, -1 for chlorine, and the nitrate stays intact. So this is one of those double replacement reactions where the ions exchanged partners, but there is no oxidation reduction. This is not a redox reaction. So then we don't have to identify any agents because there aren't any. This one at the bottom, here we have 2 nonmetals reacting. There aren't any charges involved here, but 2 nonmetals reacting is a redox reaction. Another clue is you've got something reacting with oxygen. So we have to identify oxidation states here to see what's being oxidized, what's being reduced. What's the oxidation state for carbon on the left? 0. It's an element by itself. And the oxygen? O2 is also 0. They're just elements. Elements are easy. They're always 0. Here we've got the 2 nonmetals, so we say Fa765. Fluorine, hydrogen, oxygen. What does oxygen want to be? -2. And what does the carbon have to be then? +4. Yeah. It's very simple math, and yet somehow it just can make you crazy. The good news with this question, even if you got the number wrong, you could still get the agents correct. So carbon is going from 0 to +4. Is that oxidation or reduction? Oxidation. So what kind of an agent is it? A reducing agent. The oxygen's going from 0 to -2. The oxidation state is going down. That's reduction. So if it's being reduced, then it's the oxidizing agent. I know, right? Isn't that fun? Any questions? So combustion reactions are redox reactions. They're a substance reacting with oxygen. They're going to form one or more oxygen-containing compounds. Often that will be water. In combustion reactions, combustion is burning. Burning involves the release of heat, right? So here we have an example. Natural gas is predominantly methane. So here's methane reacting with oxygen. It's going to form carbon dioxide and water. The oxygen here has a 0 oxidation state. After the combustion, it'll be -2. The carbon here, well, the hydrogen was +1, and so the carbon was -4. And over here, the carbon is +4. So the carbon is being oxidized, the oxygen is being reduced. We have a redox reaction. And this is where the word or the term oxidation came from, because the carbon is getting oxygen. It's becoming oxidized. It doesn't ever really say that in the slides. So write this down. If you have a hydrocarbon, a compound, I'll write it down too. That would only be fair. If you've got a compound containing carbon, hydrogen, and or oxygen, it may or may not have oxygen, and you have a combustion, it'll react with oxygen, and the products are always the same. So that's kind of nice. CO2 and water. So it doesn't matter what the compound is. What happened to my twos? Those are commas. Sorry, brain fart. Okay, so if you've got a reaction with something that contains carbon, hydrogen, and possibly oxygen, reacting with oxygen, a combustion, the products will always be CO2 and water. Okay. So we need to know that for this. Write a balanced equation for the complete combustion of liquid C2H5OH, ethanol. So I've been given one of my reactants, so C2H5OH, and I'm told that that's a liquid. What's the other reactant? Oxygen. And what's the formula for that? O2. And what state is oxygen? It's a gas. Okay, so there are the reactants. This compound contains carbon, hydrogen, and oxygen. What are the products? CO2 and water. So CO2, and what's the state of CO2? It's gas. And water. Now, normally we put liquid as the state of water. It's going to be a gas here because this is combustion. This is going to be hot, right? So the water's going to be in the gas state. Okay? Now we need to balance this. Did you like the tally method, or would you rather just go back and forth? Anybody have an opinion? Tally method, okay. You can do back and forth too. Okay, so tally method, we're going to just draw a line down the middle. We're going to take inventory, carbon, hydrogen, oxygen. We're going to go, there's two carbons, 6 hydrogens, and 1 oxygen there. No carbons, no hydrogens, 2 oxygens. We'll come over here. We've got 1 carbon, no hydrogens, 2 oxygens, no carbons, 2 hydrogens, 1 oxygen. Okay, I did that kind of quick. Now we're going to look at our totals here and see how things work out. So we'll do carbon first. Here I've got 2 carbons on the left side and only 1 on the right. So I'll need to put a 2 in front of the CO2. That will change all of the numbers underneath, because in 2 CO2s, now I've got 2 carbons and I've got 4 oxygens. So carbon is balanced. Here's the hydrogen. There's 6 on the left and only 2 on the right. How do I make a 2 into a 6? Multiply by 3. Put a 3 there. 2 times 3 is 6. 1 times 3 is 3. And now I've got, down to the oxygens, I've got a 1 and a 2. That's a total of 3 over here. And 4 plus 3 is 7. So 4 plus 3 is 7. I need 7 oxygens. I don't want to mess around with the coefficient on this one because that would mess up the carbons and the hydrogens. So I'd really like to only put a coefficient on this. So I've got 1 here, and then how many more do I need to get 7? 1 plus blank is 7. 6, okay? So I need 3 of these, 3 oxygens. So if I had 3 oxygens here, that'll give me 6, and 1 plus 6 equals 7. Again, very simple math, but you have to be able to visualize what it's all about, and that's the hard part. Any questions? It takes practice.